Okay, welcome back everyone. In this video, I'm going to spend a few minutes explaining how we can derive the equations of RC circuits and showing you how they're kind of similar to what you may have seen before if you've already studied mechanics. So RC circuit theory kind of starts right where mechanics leaves off in terms of a differential equation that we need to solve. So let's kind of go back and remind ourselves of what happened during mechanics. And remember that we had a situation where an object was falling that had a mass m and had two forces acting on it, the force of gravity mg and some frictional force that maybe was proportional to velocity kv. And so I'm going through some of the equations that were used in chapter 5. And so if you're only studying electricity and magnetism, you may want to go back and look to see how the book derives this. So if we were to try to solve this system for the position or the height as a function of time, well, we would find that when an object first starts off, it has zero velocity. So we could guess that when t is equal to 0, the velocity should be equal to 0, and the acceleration should be equal to 9.8. That's just kind of common sense. And we could also guess that as time goes to infinity, that the velocity is going to go to some terminal value, so vt, and the acceleration is going to be equal to 0. And at that time, if the acceleration is equal to 0, we can say that the sum of the forces equal to ma is equal to 0, and we'll say for fun that downwards is positive. So mg minus kv is equal to 0. But when a is 0, this is our terminal velocity, and vt is simply mg over k. So k has units that'll make this work. Okay, so then what we can do is kind of look at this at all times. Well, what happens in between? What happens to the acceleration and the velocity and the position, for that matter, in between these two extremes, these boundary conditions, if you will? So we write our general equation, F equals ma, and this time we have mg minus kv is equal to ma. But remember, a is actually a derivative. It's dv dt. And in calculus and differential equations, we basically need to separate the variables. And there's a variety of ways to do this. Probably the easiest way to start is to divide everything by k. And what that does for us is it gives us mg over k is something we can just rewrite as the terminal velocity. It's just a constant that's based off of whatever we plug in for the mass, gravity, and the constant. V is going to be our variable, and then m over k is another constant. And if you like, we can just separate our variables like this. And further, we want all the v's on one side and all the t's on the other. Well, I don't see any t's. All I see is k over m times dt on one side. And on the other, I see 1 over v terminal minus v times dv. So at this point, we can integrate. And to make the math people happy, I usually go from 0 to t prime, so that t prime is not the same as t. And we'll go from, we'll have to call this v initial. We'll go from v initial prime to v final prime. And let's, just to make the math a little bit easier, let's look at the special case where v initial is equal to 0. And you can always go back to this point and plug in things and see how it works. Okay, so basically we're going to have on one side, very straightforward, k over m times t prime. And on the other side, we're going to have a natural log. And there's going to be a negative sign in front of it. We're looking at the negative natural log of v terminal minus v evaluated from 0 to, let's now say that our v final has turned into v prime. Okay, and v prime is going to be our velocity at some later time. Okay, well, let's bring this negative over to here. So I have negative k over m times t prime. And this is going to give us, oh, let's see here. We're going to have the natural log of vt minus v prime minus the natural log of vt. Okay, and we remember that when we subtract natural logs, it's the same thing as dividing. So it's vt minus v prime over vt. And so that's the natural log of 1 minus v prime over vt. That's all equal to negative k over m times t prime. And at this point, I'm going to make the math people really mad, and I'm going to just write this as a t. But first I'm going to, I guess there's no good term for this, e-isize it. I'm going to raise the power of e to each side, and of course that gets rid of my natural log, and I have e to the minus k over m times t is going to be equal to 1 minus v over v terminal. Okay, bring the 1 to the other side. That's going to be equal to negative v over vt. Let's multiply everything by a negative 1. So that's actually a negative, that's a positive. And multiply everything by v terminal. And at the end of all of this mess, we have v as a function of time, assuming that v initial is 0, is equal to terminal velocity times 1 minus e to the negative k over m times t. And this is the expression for the velocity as a function of time. Okay, now I know that this is about RC circuits, so sit tight. Okay, just want to remind you of how this works for mechanics, where we have something, namely air resistance, which is impeding or slowing down the movement of our object. So the velocity as a function of time won't increase forever, it'll cap at some terminal velocity. Likewise, the acceleration is going to start at some value, well, let's call it 9.8, and it's actually going to reach an asymptotic value of 0 as time goes on. And I could do that by I could show you this by taking the derivative, so I could do dv dt to get back to a as a function of time. But let's move on to what happens with RC circuits. Okay, now in an RC circuit, you've got a battery, you have a resistor, and you have a capacitor. And we know that if this is the resistor and capacitor, we know that the voltage in the resistor is going to be equal to the current at any time times the resistance R, and the voltage in the capacitor will be equal to the charge at any time divided by the capacitance. And we must recognize that both the current and the charge are functions of time. And the other thing that we're going to find out is that the current actually kind of corresponds to acceleration, and the charge corresponds to velocity, at least in the way that it behaves. And remember that the current is actually a derivative of charge as a function of time, just like acceleration is a derivative of velocity. Okay, so how could this possibly be the same mathematically? Well, we go back to our loop rule, and we know that in a loop the sum of voltages is equal to 0, and so we go around in kind of a normal fashion. First we come to the battery, which is a positive value. We go through the resistor and we lose IR, and we go through the capacitor and we lose Q over C, and that's got to all be equal to 0. Okay, now if you want to think about this in terms of F equals ma and things falling, well then what we can do is bring I to the other side and say that E minus Q over C is equal to IR. Okay? Compare this to mg minus kV is equal to ma. Now hopefully you can see the comparison. Because if I write this first equation in terms of Q and dQ, I'm going to have E minus Q over C equals dQ dt times R. And that's exactly the same as writing mg minus kV is equal to m dV dt. Exactly the same mathematically. So I'm not going to take as long to explain how the math works for this. Essentially what we have to do is we're going to, sorry, brain fart. So we're going to multiply everything by the capacitance C. So we're going to have CE minus Q equals RC times dQ dt. So now you have the first glimpses of where the time constant 1 over RC is going to come from. We're going to separate our variables. So we have dt CE minus Q equals RC dQ. And of course we need to have the Q's on the same side. So we're going to have dQ over CE minus Q is equal to dt over RC. And again, we're going to integrate from 0 to Q prime and from 0 to T prime. And in this, we're going to assume that Q initial is 0, much like we said that V initial was 0. And so again, we're going to get a natural log. And we have to evaluate from 0 to Q prime. And on the other side, we're simply going to get minus T over RC, T prime. Now the minus sign is because when I had a minus sign with the natural log, but I just brought it to the other side. Okay, and so when I substitute, I'm going to have natural log of CE minus Q prime over CE is equal to negative T prime over RC. I'm going to drop the pretense of the primes and raise each side, or e to each side's power. And essentially I'm going to get 1 minus Q is equal to, let's see, whoops, 1 minus Q over CE, sorry, is equal to e to the minus T over RC. And when we solve this for Q as a function of time, ultimately what we get is CE times 1 minus e to the minus T over RC. And so there is the current as a function of time. I'm sorry, the charge is a function of time. I was just thinking if we want to get the current as a function of time, we have to take the derivative of that. And so we have a constant that we leave alone. We've got 1 turns into a 0. And then we have plus essentially RC times e to the negative T over RC. And let's see, how's this going to work out? Oh, I'm sorry. I totally forgot how to do a derivative. It's going to be 1 over RC. Okay, so that means that the current as a function of time, the C's are going to cancel. It's going to be E over R, e to the minus T over RC. Okay, and this gives us behavior for the charge that looks exactly like the velocity. Starts at 0 and goes up to some maximum value CE. Okay, so we're talking about the charge on the capacitor. Okay, that's a horrible graph. That's slightly better. And for the current as a function of time, That's going to start at 0, and I'm sorry, the current in the resistor will start at some value and decrease rapidly. So this is acting like acceleration, and this is acting like velocity. Okay, so it took a little while, but we were able to show how RC circuits are very similar to air resistance in terms of the math. So now you can use these for solving all sorts of different types of problems.